The last topic that we are going to cover in chapter 12 is fluid dynamics, which concerns fluids in motion. Now, fluid dynamics is a very difficult subject, and it's an area of active research, and there are many unsolved problems in fluid dynamics. However, one thing with fluid dynamics is that mathematically it's notoriously difficult. However, for the purposes of this elementary course, we are going to make a bunch of assumptions, and that will get rid of all the complicated stuff. And ultimately, it's just going to be two simple equations. So you have nothing to worry about for this course, but in general, I just wanted to make the point that fluid dynamics is a very, very, very complicated subject. Okay, so let us make a few assumptions regarding fluids. And once we make these assumptions, we're going to call the fluid an ideal fluid. So ideal fluid is a fluid which satisfies all the assumptions which I'm about to state. Okay, so the first assumption that we're going to make is that the flow of the fluid is steady. So what does that mean? Suppose you have a pipe, and the pipe does not necessarily have to have a uniform cross section. Suppose you have this pipe, and there is some fluid like water flowing through the pipe. If you just keep track of the velocity of the fluid at this point, you'll find that the velocity at this point is fixed. That is what steady flow is. So if you just keep track of the velocity at one point, any point in the fluid, you'll find that the velocity is fixed. You might find that the velocity at this point, so let's say that the velocity here is 3 meters per second, always. You might find that the velocity here has a different magnitude and direction. Maybe it's 5 meters per second in a different direction. But here too, if you keep track of the velocity over there, you'll find that it's the same velocity all the time. So steady flow means that the velocity of a fluid at any fixed point does not change with time. Now, there is another related concept here. If you now follow a tiny element of fluid as it's moving along, suppose this is the path taken by a tiny element of fluid as it's following the flow. This path is called a streamline. I'm just mentioning these. We are not going to use these concepts in what we're going to do, but I'm just mentioning these because you might hear these terms in a more advanced course. Okay, so a streamline is the path taken by a massless fluid element, a tiny element of fluid. You can just think of it as like a water molecule or a molecule of the fluid that's flowing along with the fluid. So the path taken by that is what we call a streamline. Okay, the next assumption is that the fluid is irrotational, which means that if you place a paddle wheel anywhere in the fluid, like this paddle wheel over here, the paddle wheel might be carried along as a whole, but it will not rotate. So what that means is that the fluid does not have any eddies or whirlpools in it. And there's a reason we are making this assumption. It's because eddies and whirlpools are extremely difficult to analyze mathematically. So that's the reason that we just assume them away. Okay. The next assumption is that the flow is non-viscous. That means that the fluid does not have any viscosity, so there is no fluid friction. You know that different fluids have different amounts of viscosity. You know that honey is a very viscous fluid. Water is in comparison to water. Water has some viscosity. Alcohol has less viscosity than water. Liquid nitrogen, if you've ever seen it, has very, very low viscosity. So if you ever see liquid nitrogen, and I could have showed you this in class, if you just give it a stir, it will just keep on rotating for a very, very long time, unusually long time. So different fluids have different amounts of viscosity. We are just going to assume that our fluid has no viscosity. So the flow is non-viscous. And finally, we are going to make one more assumption, which is that the fluid is incompressible. And that is actually a good assumption for liquids, because most liquids are incompressible. But it's not a very good assumption for gases, because as you know, gases are quite compressible. Okay. So a fluid that obeys all of these assumptions is called an ideal fluid. And once you have an ideal fluid, you can write down two equations, which we're going to discuss now. The first of these two equations is called the equation of continuity. All right, so let me explain the equation of continuity. Suppose you have a pipe with a varying cross-section. Let's say that the area of the pipe over here is A1 and the area of the pipe over here is A2. Okay. Let's say that the velocity of the fluid over here is V1 and the velocity of the fluid over here is V2. All right. Now, the equation of continuity says that A1 V1 equals A2 V2. So if the cross section of a pipe is changing, then the velocity of the pipe will also, velocity of flow through the pipe will also change. And in general, where the cross section is smaller, the velocity of the flow will be greater, right? So the product of A and V is constant. So if A goes up, V will go down, and if A goes down, V will go up. I'm just going to quickly explain why this equation is true. It's very easy to see that. Consider an amount of time, delta t, a small amount of time, delta t, right? So in time delta t, suppose you have a water molecule over here. In time delta t, how far will that water molecule move? Let's say that it moves from here to here in time delta t, right? What is this distance going to be? The velocity here is v1, and delta t is a very tiny interval of time. So the distance that the water molecule will cover is going to be v1 times delta t, right? So in time delta t, a cylinder of water, which looks like this. So since this applies to every water molecule at this face, a cylinder of water of length v1 times delta t will have moved into this section of the pipe, right? Okay. Now, in the same amount of time delta t, a cylinder of water of length v2 delta t will have exited this length of the pipe from the smaller end, right? Now, a fluid is incompressible. That was one of our assumptions. So that means that the volume of fluid that entered at one end has to equal the volume of fluid that exited at the other end, because otherwise some fluid would have to compress in order to make room for it. So if 10 cubic meters of water entered on the left end, exactly 10 cubic meters of water has to exit on the right end in order to make room for it, because it's not possible for water to squeeze and make room. So from there, Since the fluid is incompressible, volume of fluid entering on the left is equal to the volume of fluid exiting on the right. Let's calculate the volume of fluid entering on the left. So that's just the volume of the cylinder, which has length V1 delta T and area A1. So it's just going to be A1 V1 delta T, and on the right that's going to be A2 V2 delta T, and then if you just cancel out the delta T, you get the equation of continuity. Right. Now you can, if you multiply both sides by the mass, then this equation just says the mass of fluid entering on the left is equal to the mass of fluid exiting on the right. That's also another form of the continuity equation. Okay. All right. In general, this quantity A1 multiplied by V1 is called the volume flow rate of a fluid. So it tells you how many cubic meters of the fluid are flowing past that section of the pipe per second. So that's the volume flow rate. I should just say A multiplied by V in general is called the volume flow rate. And you know that if you multiply volume by density, you get mass. So rho times A times V is called the mass flow rate. So that just tells you how much mass or how many kilograms of fluid are flowing past that section of the pipe. Okay, so the equation that we just derived, A1 V1 equals A2 V2, is our first important equation, the equation of continuity.